11 again, but the second part. Okay, and for the second part, we stopped right here. Okay, we are going to solve problems related to static equilibrium. Then, when forces both have vertical and horizontal components, in order to be in equilibrium, we need to have net forces in the x direction equals zero, the net forces in the y direction equals zero, and the net torque also is zero. Then I should apply the three conditions here: sigma fx equals 0, sigma fy equals 0, sigma torque about an axis should be 0. And I should here include all the forces, and therefore I should also have free body diagrams. But what is really different here is our free body diagrams should include also distances. Okay, I want you to look here at this example here where I have a uniform metal rod with mass of 3.7 kilograms and a length of 1.2 meters is attached, which is this one here, this one. It is attached to a wall by a hinge at its base. Now, maybe in this one, we will talk a little bit about it, but I want you always to know that whenever you have a hinge, there is a force that is acting at that hinge. In general, we are going to assume it in a direction that is, maybe this is the one, I most of the time I will call it R, and that R should have an Rx and Ry component. Okay, and sometimes you will not be able maybe to correctly find its direction, and never mind, your solution will not be wrong. The only thing that is going to change is you're going to have a negative, and then you know that you need to switch the direction. A horizontal wire bolted to the wall 0.51 meter above the base of the rod holds the rod at an angle of 25 degrees above the horizontal. The wire is attached to the top of the rod. Find the tension in the wire, find the horizontal and the vertical components of the force exerted on the rod by the hinge. Okay? These are the steps of the solution. The first thing is, what are the forces acting on the beam? Okay, and this is the thing that I will do here is I need to redraw the beam, isolate it from maybe many things in there, and I will find like what are really the forces on that. If I have angles, I need maybe to write them on the diagram. I like to do this. And also, like usually what I will do is I will say this is like at L over 2. Remember, the weight, if it is considered to be uniform, is going to be acting midway. Okay? I need to, like sometimes I might start with sigma fx and sigma fy, and sometimes I will start with the torque equation. Remember, for the torque equation, it doesn't matter where you are going to locate your axis of rotation or your reference point for calculation torques. This is completely arbitrary here, but I did choose it here because I have Ry and an Rx. They are not known, and I want to get rid of them. How can I get rid of them? They don't have any torque when they are going to go through the axis of rotation, because their distance is going to be 0. And this is the reason why I did this. Now, I can repeat my question with having my torque calculation at any other point, but this is going to be much more complicated than this one. Okay? Now, calculate the torque at O, which is this point. Is going to be here the two torques, the one from the tension and the one from the weight of the the beam itself. Here, T, the force, times, like, it is located at L from 0 and sine 25, minus mg, which is the weight of the beam here. L over 2, it is the location of the center of mass, sine 65, which is 90 minus 25 equals 0. Then I can rearrange my terms and find T equal 39. Now, the second part, they are asking about Ry and Rx. I can simply say here, sigma Fy should equal 0. The only forces that they are acting vertical is Ry and Mg. Then Ry, maybe I want to write here my Y and my X. This is my positive. I like to consider my positive up and my positive for the X to the right. Then Ry minus Mg equals 0, and Ry is going to be the weight of the beam, and Rx minus T equals 0. Then the tension is going to be the same as Rx, and Rx then is going to be 39. This is the same problem here. And here we are going to get the very famous problem, which is called the ladder problem, where you might have like many versions of this ladder problem. Okay? Okay, and now we are going to try to solve this one. Consider a ladder with a painter climbing up it. If the mass of the ladder is 12 kilograms, the mass of the painter is 55 kilograms, and the ladder begins to slip at its base when her feet are 70% of the way up to the length of the ladder. What is the coefficient of static friction between the ladder and the floor? Assume the wall is frictionless. Actually, I did a mistake in the calculation. I made this not 70, I made it 75%. And then you will find the solution in the video 70%. For me, I'm going to keep it at 75. I don't want to change my numbers because it doesn't matter, okay? All right, here the free body diagram with distances on it and my axis to the right, to the left here. I have a normal force, and that one, it is from the wall and is going to be to the west or to the left. I have, this is the weight of the painter and this, or the person, and this is the weight of the ladder. And I have, of course, also, like from pressing on the air, on the ground, we have normal, we're gonna call it normal 2. And in order to prevent the ladder from slipping, we will have this Fs maximum. Now mlg, which is the weight of the ladder, is acting at L over 2, and mb, the painter weight, times g, the painter weight is acting at 0.75 L, which is 3 over 4 L. I can say, I can apply sigma Fy equals 0, and that is going to be N2 minus mlg minus mpg equals 0, and N2 equals 12 plus 55 times 9.8, which is 657 in newtons. For the x, sigma Fx equals 0, we have Fs maximum minus N1 equals 0, then Fs max equal normal 1. Now the torque equation. Now every torque is going to be a sine, is going to be a force, is going to be a distance, is going to be sine and angle. All right? And in my case here, for normal 1, which is the first force here, it is normal 1 times L times sine theta, and my theta is here, minus mlg, L over 2 sine 90 minus theta. Okay, why it is negative? Because remember, for the torque, I said in order to find the direction, okay, you need to have your R unit vector this way, and then you're gonna bring R to the force. Then this is negative, clockwise, this is negative. And for N1 is gonna be positive. I did choose my O here so that N2 and Fs maximum, they don't have any torque, they're gonna be 0. Now, also, I will say minus mpg times L 3 over 4 sine 90 minus theta. You will find my solution a little bit different from the video one, and I want you to be open to having more than way of solving the problem. Now, this is these distances they were given. This is 4 and this is 3, and we know from the Pythagorean that this one should be 5. Now, sine theta is going to be the opposite divided by the hypotenuse, and sine 90 minus theta, which is this one here, is gonna be again its opposite divided by the hypotenuse. I put here my signs, and then I was able to calculate N1 as 3, 4, 7. And then I got my equation that I got from sigma fx equals 0. And I know Fs maximum is mu s times normal 2 and equal normal 1. And from that, I got my mu s to be 0.529. All right? Then this is the minimum that after that, like, the ladder is going to slip. We know that, of course, for extended objects to be balanced, it must be supported through its center of mass. Okay, then I will say we can find the center of mass by having, just as a very easy experiment, you will suspend your object from a point, and then you will draw a vertical line like this, and then you will suspend it from another point and find also the line that, like, there's a string, and with a mass usually you're gonna put a weight here, and then when they're gonna intersect, this is gonna be the center of mass. If your object is uniform, then the center of mass is going to be at the center of the object. Here I have 0.34 kilogram meter stick balances at its center. If a necklace is suspended from one end of the stick, the balance point moves 9.5 centimeter toward that end. Is the mass of the necklace more than, less than, or the same as the mass of the meter stick? Explain and find the mass of the necklace. Of course, it's not going to be the same, and I will say if we will find first initially the center of mass of the ruler by itself is going to be at the 50 centimeters, okay, and then it was shifting 9.5 centimeters, then I will say the mass of the necklace times G times 50 minus 9.5 should equals the mass of the ruler times G times 9.5 centimeters. And from that, I can find that Mn should be 0.080 kilograms, which is 80 grams. For the dynamic applications of torque, when we are dealing with systems that have both rotating parts and translating parts, then here I will say this is a translating, okay, object, and this one, it is rotating. Then I need to draw a free body diagrams for both. I need to apply a Newton's second law for both and solve the two equations together. Let's try this. I have, okay, ignore this because I'm not using my positive downward. I'm using my, I'm using my X and Y as always. Like I don't change it. A 2.85 kilogram pocket is attached to a disc-shaped pulley. Why this is important is because knowing that it is a disc, it is moment of inertia, it is 1/2 mr squared. And you're gonna get these from your table in the textbook. Radius is 0.121 meter and the mass for the pulley is 0.742 kilogram. If the bucket is allowed to fall, what is its linear acceleration? What is its what is the angular acceleration of the pulley? How far does the bucket drop in 1.5 seconds? And sometimes we might ask you also about the forces, like calculate the tension or something like this. Again here, I did draw I have two objects, one linear motion and the other rotational. I did draw here the free body diagram for the translational motion and my acceleration downward for this one because it's gonna fall. For the pulley, it is my rotational object. I did put here normal and mg because I know that these forces are there, but their torque is 0. But if I will ask you to draw a free body diagram for a pulley, you know that there is the weight and there is the normal, but I will say they don't participate in the torque. The only one that is going to create the torque is the tension. And here I can say that the tension, this is my R, is going to create a negative, okay, let's say torque. Apply Newton's second law. This is for the bucket. Sigma F equals MA, and then T minus mg equals minus ma. And here A is the linear acceleration. We're gonna apply Newton's second law for the pulley. Sigma torque equals I times alpha minus TR, the torque, it is the torque, the sign negative, T, the force, times R, the distance, sine 90. Sine 90 is 1, and this equals minus I times alpha. Then the T, from that one, I can get it as M over 2 times A. I can combine the two equations here and find A, and like just here, I did choose T equals M over 2 times A, and I put it into this equation, and I plugged my numbers, and then A is 8.67 meters per second square. This is the magnitude of the linear acceleration. For A, it is R times alpha, and it's going to be A divided by alpha is going to be A divided by R, which is 8.67 divided by 0.121 meter. And this is going to give me 71.7 radians per second square. Finally, here is going to be kinematics. I want to find what is really the Y. T is 1.5 centimeters. The initial velocity is 0. And the acceleration, since the bucket is accelerating downwards, it is negative. And then I'm going to use my kinematic delta y equals v0t plus 1/2 at squared. And you know that my initial velocity is 0. Then I will be able to calculate my delta y, okay, negative 9.76. And I know y minus y0 equals 9. And since it was really from y equals 0, then my y is negative 9.76. Another quantity that we want to introduce, which is angular momentum. And the definition of angular momentum, it depends if my object is continuous distribution of mass, then this is if it is continuous distribution of mass versus if it is a particle. Then when it is at continuous distribution of mass, we use L equals I omega. When it is a particle moving in a circle that has a radius of r, is going to be RMV or r times the momentum. The unit, it is kilograms meters per second, meters squared per second. Now, in general also, remember, we can say L equals RP sine theta, which is RMV sine theta. And again, the unit is going to be the same. And then here I'm going to consider also, again, the quantity that is perpendicular to R. Again, here we can, remember we said before, force is related to change in momentum over time or the rate of changing momentum. We can also have a Newton's second law for rotational motion. Tau is I times alpha, and it is the change of angular momentum per unit time. Then if my torques, the external torques are zero, then I will say, I can say my Li should equals my final. Then the angular momentum conservation is going to be valid whenever I have the torques, the net torques equals zero. Okay, we know all about figure skaters when they spin with their arms extended. When she pulls in her arms, she reduces her rotational inertia and spins faster so that her angular momentum is conserved compared to her initial rotational kinetic energy. Her rotational kinetic energy after she pulls her arm must be larger because she's rotating faster. Because remember, K is 1/2 I omega squared. This is the more effective in the kinetic energy because it appears as squared. But it is just linear. Then this is the reason why it's going to be more effective. As the moment of inertia decreases, the angular speed increases, so the angular momentum does not change. And here we have like two disks. One of them is rotating at omega 0, and here I have the second is dropped with omega equals 0, and then they're gonna move together with omega final. I know here that Li should equals L final. We are going to try to use it here using a figure skater that can increase her spin rotation rate from an initial rate of 1 revolution every 2 seconds to a final rate of 3 revolutions per second. If her initial moment of inertia was 4.6 kilogram meters squared, what is her final moment of inertia? You don't need here to make conversions in units, because when it is like equal on both sides, you can drop these conversion factors, then you can keep them in revolutions per second. But you have to pay attention here that point, omega 0 is 1 revolution in 2 seconds, then it is 0.5 revolution per second. I did make here Li equals L final. Then omega 0 I 0 should equals omega I, and from that I can find that that I is going to be 0.767 kilograms meters squared. For the sake of significant figures, I rounded 0.77. Here we have another question combining both continuous objects and also particles. A student sits at rest on a piano stool that can rotate without friction. The moment of inertia of the student's stool system is 4.1 kilograms meters squared. A second student tosses a 1.5 kilogram mass with a speed of 2.7 meters per second to the student on the stool, who catches it at a distance of 0.4 meters from the axis of rotation. What is the resulting angular speed of the student and the stool? Now, initially, I have them like at rest. Okay, then I will say when I will calculate Li equals L final. Okay, for the mass that was tossed by the second students, it has Li equals MVR. And when that mass is gonna go to this tool and they're gonna rotate together, this is the moment of inertia of the student stool system. And this one for a particle that is at a distance r from the axis of rotation, it is mr squared. And both of them, they're gonna rotate with an omega final. I plugged in here the numbers, 1.5 times 2.7 times 0.4. This is the initial moment of inertia, 4.1 plus 1.5. And that, mass is at 0.4 meters from the axis of rotation times omega final. And then I was able to calculate my omega final to be 0.37 radians per second. We can apply the same physics to rotational work and power and have the analogies again between things. If you remember, work is force times delta x, or we did call that D. And here the same thing, we will say the work is tau times delta theta. And also we can say that the work energy theorem applies also, then work equals change in kinetic energy. And I will say this is the total work should be 1/2 I omega final squared initial squared. Now, power, it is the rate at which work is done for rotational motion as well as for the translational motion. Then I can derive P equals tau times omega, very similar to linear form, which is FV. This is the instantaneous power. We know, of course, that we have here angular velocity. It's a vector, and it is along the axis of rotation. How we gonna decide that? It is by using the right hand rule. And remember always the right hand rule, then you are going to have your fingers curling in the direction of the rotation, and your thumb is gonna point in the direction of the omega. And also, since L, the angular momentum, it is I, which is a scalar, times omega, then is going to have the same direction as omega. Also, torque, remember, we said it's a vector quantity. Okay, usually we use the plus and the minus from the torques, like the clockwise, but the actual direction of the torque is going to be determined also by the right hand rule. You curl your fingers in the direction of the rotation, and your thumb is going to give you the direction of the torque. Now, also, conservation of angular momentum means that the total angular momentum around any axis must be constant. And this is why gyroscopes are really so stable. And the gyroscope in operation with freedom in all three axes, and the rotor will maintain its spin axis direction regardless of the orientation of the outer frame. We will learn more about it in Physics 201. All right. Okay, just here. I want you to, read here the summary of the chapter with all the equations here. It is very helpful to you. And That's it for